This is lesson 24 of our A-level physics no-nonsense lessons. And this one is all about refraction of a light. Refraction of light, and it's the first lesson of the new topic of optics. Okay, good start. So let's get on with it. There's three things that light can do, well, that any wave can do, when it reaches a boundary. So to take light for the context, a boundary between two different media, which is just stuff that light can move through, whether it's a vacuum or air or glass or water, plastic, doesn't matter. There's three things that can happen. Let's just make a note of these here. Three things light does when incident, it's a technical word which means comes in and hits it, on a media, maybe that's just the stuff that the light moves through, boundary. And what are those three things? Light can be transmitted. Let's write it as transmission. It can be reflected, call that reflection. And it can be absorbed, let's call that absorption. And it's really malfunctioning again. Now, does absorption have a P or a B? Absorption. I think it's one of those funny ones that's spelt differently to how you'd expect it. If that's wrong, hey, get in the comments. Let's pretend it's deliberate. So remember some of these definitions. When we say incident, we mean light goes and hits the boundary. And when we say media, we mean the stuff the light gets through, but it could be a vacuum. Okay, so we're going to focus on transmission. We're going to focus on the light that gets into a second medium from a first medium. And that transmission can cause refraction. Now, there are some subtly different definitions of refraction. Some people would define refraction as the changing of direction of a ray or a beam of light when it enters the boundary at some angle to that boundary surface. Others would talk about refraction just being the change in speed of the light, and it causes the change in direction, but refraction isn't an aim of the change of direction. I think with A-level exams, we tend to come down on the idea that refraction is the change of direction. So you don't always get refraction with transmission. And you don't get refraction with transmission if the angle of incidence is 0 degrees. So let's just make a little note of that. We're going to focus on transmission today, and importantly, we're focusing on refraction. And we say that there is no refraction if angle of incidence is equal to 0 degrees. At least that's what we say. Okay, so at GCSE level, you did meet the idea of measuring angles of incidence and what that means. So let's draw a quick diagram by way of a reminder. If I have a boundary between two media here, and I could label this top one here medium 1, medium 1, and this one down here, medium 2. Then what we're saying is that there is a beam of light. Now we're going to represent the path of that beam by using a ray. A ray it has 0 width, but a beam can have some width to it. The light is actually a beam, but all beams spread unless they're spatial solitons, and you don't do spatial solitons at A level, so forget I said that. Unless you're really interested, then look it up. Apart from situations where you've got media that are nonlinear and produce spatial solitons, all beams of light will spread. Even the straightest and narrowest and most well-collimated beam of light will spread. But rays just represent the direction that the wave energy is being transmitted. And in this case, it's light. So the direction of the light wave is represented by the ray. And we might have a situation where the ray changes direction, like this. Now, whenever we draw rays, we have to do arrows to indicate the direction of energy flow, just like that. So those are our rays. And you probably remember from the waves topic that wave fronts are always going to be perpendicular to the energy transmission direction. So we'd have a bunch of wave fronts, which for some reason it's not letting me draw. I do not know what's going on with that. Yes, you may remember that the wave fronts are always drawn perpendicular to the rays, to the direction of energy transfer. I'm just drawing these wave fronts like this, where the distance between wave fronts is going to be the wavelength and the wave fronts there. So the width of those wave fronts would indicate the width of the beam of light. And we end up with a situation like this. And now the wave fronts are closer together, just like that. And I'm not going to draw all of them because I can't be bothered. So we've got the blue part, which is the wave fronts, and they are perpendicular to the ray. And we've got the ray, which indicates the direction of the beam, if you like, the direction of the wave energy. So that's the ray, which is the direction of the light. Direction, that's direction of, let's say, energy flow or propagation. There's lots of words that we could say to describe this. And there we have it. That's our simple diagram that shows refraction, and you will have done that at GCSE level. We also have to draw a normal, which you will have done at GCSE level. The normal being a line that is perpendicular to the media boundary, passes through where the rays are incident on the boundary. So that there is our normal, and I will draw a little 90 degree here to indicate that. A little arrow here, it's going to get very complicated. Normal, which is 90 degrees to the boundary. So we can get very complicated diagrams like that. We're just going to focus on part of that diagram. So let's redraw it and let's make it a little bit easier. Let's redraw it and let's just draw the rays and the media boundary and the normal. So this is medium 1, this is medium 2. I'm not going to bother writing medium each time. We've got our rays. I'm going to carry on with the same sort of color notation, where this is red coming in. Try that again. Red, try that again. Red coming in, and then red coming out. So the ray that comes in is referred to as the incident ray. The ray that comes out is the refracted ray. So this is incident ray, and this is refracted ray. A lot of students at first get refracted and diffracted mixed up. I've heard it pronounced diffracted before, And that can help, refracted and diffracted, although I don't think I would pronounce it like that. But, you know, there's nothing wrong with pronouncing words a bit oddly if it helps you make sure you don't write the wrong one. Diffraction, spelled with a D, is not refraction with an R. They are different words referring to different phenomena. So there's our normal. So let's draw our angles in here. We have an angle measured to the normal here and an angle measured to the normal there. Now this angle measured to the normal, I'm going to call it θ1 because it's in medium 1. And this one here, I'm going to call θ2 because it's in medium 2. Now in this particular case, θ1 has a special name. In this case, because of the direction of the arrows, the red arrows, θ1 is the angle between the incident ray and the normal. So we're calling that, in this case, the angle of incidence. But it is important that you know that this is only in this case. If the ray was traveling in the opposite direction, the arrows were all in the opposite direction, then θ1 would be the angle of refraction. In the way we've drawn it here, θ2 is the angle of refraction. And they have, and this is in this case. Now they have a lot of different symbols we could use for them. So in this case, we're saying θ1, but we could have called it I for incident angle, or angle of incidence, or we could have called it θi. Notice the I have a little squiggly I to make it a little bit easier to see what's going on. No, it's an I, not a number 1. θ2, in this instance, is our refracted angle, and sometimes you'll see that written as R, although R could be the reflected angle, the angle of reflection. So sometimes you'll see it as θr, but again, that could be a reflected angle. So sometimes you'll see something like θt, where the T stands for transmission. So the point is, you've got to be careful of your notation, and you've got to make sure you are consistent, and you've got to be clear with the examiner or anyone that's trying to read this what your notation represents. Define everything. Be careful with notation. Now, people who may have studied the IGCSE will have met a version of Snell's law. GCSEs now don't tend to include it, but GCSEs used to include it, which was written as N equals sine I, let's try and do the I right, sine I divided by sine R, where N was the refractive index. Refractive index. There's actually a better definition of N. It is a refractive index, but it is the speed of light in some sort of medium underneath the speed of light in a vacuum. So it's speed of light in a vacuum divided by the speed of light in some sort of medium. That's a better way of defining it. And we will come on to refractive index and what it means. We'll come on to that probably next lesson. I'm going to put this S, or maybe I should put M for medium. Sometimes we just use the notation we want for that time. And C0 is the speed of light in a vacuum. Speed of light in vacuo. And this one here is going to be speed of light in medium. Now, obviously, the speed of light, well, I don't say obviously, because you might not know this. This is a statement of fact. The speed of light in a vacuum is the fastest speed in the universe. I'm ignoring things like galactic expansion because matter cannot move through space faster than the speed of light. It can't even travel at the speed of light. Just a little bit less than 300 million meters per second. It's a very fast speed indeed. But when light travels through glass, it slows down to about 200 million meters per second. So it's slowed down by a factor of 1.5. Ends up 2/3 of what it was. Slowed down by a factor of 1.5, or to a factor of 0.67, I guess. Yeah, that's something that you need to be aware of. So the refractive index can only ever have a value that is 1 or greater than 1. It can never be less than 1. Now, I say that, but my first PhD was looking at negative refracting metamaterials, where by use of clever metamaterials, we were able to make refractive indices that were in fact negative. And what on earth does that mean in the context of what we're doing here? Not much, because you haven't learnt the difference between phase velocity and group velocity. And all of that comes in year 14, 15, and 16 of your physics education. Let's just deal with year 12 and 13 first. Let's just deal with A-levels. And we'll worry about undergraduate physics later. So, refractive index. Here it is. And if it's medium 1 that we're interested in the refractive index of, then instead of m as a subscript, we'd write the number 1. And if it's medium 2, we'd write the number 2. You get it. And the equation that you might meet is the equation on the left. But that is very bad. It's a wrong equation. It's got a problem. And the problem is that it only works in a few cases. It only works for light traveling into a medium by leaving a vacuum. Now, we could actually say that, leaving a vacuum, we could actually say that air is a very similar refractive index to a vacuum, so you can get away with saying or air, I suppose. But that there is important. That is our... let's just draw a box around this as well. That there is important in the red box, because that is our version of what we call Snell's law, which you learn about in GCSE level. And that there I've drawn a box around in blue is our definition of refractive index. That is good. We can be happy with that one. That works. Let's use a tick. There we are. But we do have to be careful with notation and so on and so on. So there is a better version, which I'm not going to go into right now because we're going to derive it in the next lesson. We can have some success with this equation, just if we remember things like if we're leaving to go into a vacuum, we have to switch the I and the R around. That's one way of trying to think about it. We can have some success with mind games like that, but we're still, if we were trying to look at the path of light from water into glass, this equation's no good. One of the media has to be a vacuum, and n always has to be 1 or bigger. So that's something we just have to be a bit careful of. But I don't want to do too much on this lesson, because otherwise we won't have anything to talk about next lesson. So let's just talk about one last thing, which is some basic geometry. So let's just talk about geometry. And then we'll improve on Snell's law next lesson. So this thing that I'm about to draw is a rectangle. I know, how complicated. It is a rectangle. And when we have our light incident on a surface of this rectangle, now as long as the outside medium is the same all the way around and the inside medium is the same, so I got too quick in changing my color. Let's go back to this and let's call outside medium 1 and inside medium 2. As long as that is the case, then we can see that the ray that comes in will be parallel with the ray that comes out, but they will not be in exactly the same line. No, because there's refraction in medium 2. Now, in the case I've drawn here, in medium 2, it's got a higher refractive index, causing the light to slow down. So we're going to say that this is the case where N2, that should be a pen, this is the case where N2 is greater than N1. If it was less than it, then it would the refraction would happen in the other direction. So we have this going on there, we've got this going on, draw the arrows there, and we've got this going on there. We're going to draw our normals. I think we're using green for normal in our color notation, weren't we? Yes, we're using green for normals. So let's draw a normal here. Oops, that's not a straight line tool. Let's draw our normal here, and let's draw our normal here. And now for some geometry that's going to absolutely blow your minds. Let's zoom right in. Let's zoom right in so we can see it very clearly. This angle is exactly the same as this angle. They are the same. And this angle here is exactly the same as, I've lost it. I zoomed in too far and I got lost on my page. It's exactly the same as this angle. So we could use a double angular symbol for that and a double angular symbol for this. Fine. Let's label these. Let's just put this back to fit width and lock the zoom level. So this one here, which we can call θ1, we could also call θi, or just I, because it's the angle of incidence on the first boundary. So maybe we can call it I1. Then θ2, this is the angle inside here, we could call the refraction in the first boundary. But then when we come down to here, this is still θ2, that's the same angle, but now it's the angle of incidence at the second boundary. And this angle here is θ1, it's the same angle as θ1, you can measure it, it's the same angle, but that's now the refraction from the second boundary. So for rectangles, rectangular, let's say blocks that the light is going through, we can see that I1 is going to be equal to R2. We can see that R1 is equal to I2. But importantly, we could just choose to use θ1 and θ2 and not bother with whether it's angle of incidence or angle of refraction. Look, if the ray went in exactly the opposite direction, θ1 would still be θ1, θ2 would still be θ2, and we're all happy. There's no issues. So we can use sin I over sin R for the first boundary, but then we've got to be a bit careful for the second one. So we can say that N2 is going to be equal to sin I over sin R, but it's going to be sin I1 over sin R1, as long as, and this is if N1 is equal to 1. In other words, if it's a vacuum or if it's air, which is pretty much 1. But then we can say that N2 is also equal to, and this is where it gets complicated, you see, sin R2 over sin I2. Now we've swapped this I and the R over, but if you do it in terms of the theta notation, it's the same equation. And again, this is only if N1 is equal to 1. But look at that, it's the same equation. Sin θ1 over sin θ2 is equal to N2 if N1 is equal to 1. The only other thing I've got to talk about is triangular prisms. I'm just going to talk about this very, very briefly. In situations where we've got triangular prisms, the normals don't line up. So we do have to be quite careful when we draw our diagram. Well, that's a funny looking prism, but there we go. If we have a ray of light coming in, it's going to refract towards the normal, which is going to be that way. And we can draw our normal using our color notation like that. There's our normal, 90 degrees, and you can clearly see that we have our angle of incidence greater than our angle of refraction if the beam is refracting towards the normal, because the prism is has a higher refractive index than the air. Fine, but then what happens? Well, now the ray is emerging from the other side. So it's not going to follow a straight path like that. It's going to refract away from the normal, which actually bends it down here. So let's draw the normal first before I draw that, so you can see why it's away from the normal. So here's our normal drawn there, 90 degrees. That's the normal for the second boundary. Maybe I should label this normal 1 and normal 2. So normal 1, you can see I'm happy with. Normal 2 is right there, where the ray will not follow a path on its original path. It's going to refract away from the normal. So greater angle of refraction than angle of incidence for the second boundary, for boundary 2, just like that. And you can see that very clearly. So we're towards the normal at the first boundary, away from the normal at the second boundary, and because of the shape of the prism being triangular, it causes the ray to be rotated clockwise at the first boundary, but then clockwise again at the second boundary. So what? Well, if you use white light, you can use this to split the colors, because actually the refractive index for glass depends slightly on the wavelength of color that passes through it. The wavelength of light that passes through it, the color of the light that passes through it. Right, I'll tell you what, we'll stop there. This is the first lesson on refraction of light. And we will move on to Snell's law and the derivation of Snell's law and a better way of expressing Snell's law next lesson. So I hope you tune in for that. It's a good lesson. And it's really important before we move on to things like total internal reflection.